Alright, so this is going to be a video on probability of composite events. So, alright, let's say we have two events. Event A is equal to Alice owns a dog, and event B is Alice owns a cat. Now these events, they're not mutually exclusive nor independent. One could be true, both could be true, neither could be true, and they don't necessarily influence each other, but they may. Okay, so suppose we analyze data that's similar to a person like Alice, and we get some probabilities. After analyzing that data, we find that probability of event A and B is equal to 0.3, and probability of event A and not B is equal to 0.2. So we need to find probability of A. Well, the wrong way to do that is right here. Probability of event A and B is equal to the probability of event A times probability of event B. This does not work because it's not independent and not mutually exclusive. It's composite. So, all right, notice how these two events, X and Y, are mutually exclusive. All right, so event X is equal to A and B, and event Y is equal to A and not B. So only one of these can be true because they're mutually exclusive. You can see that, right? You know, B, it's either B or not B. All right, so A is equal to A and true for any event A. So let's look at this in examples. All right, suppose event A is equal to Alice owns a dog, and suppose event B is equal to the sun will rise in the east. All right, this is equal to saying Alice owns a dog because we know the sun will rise in the east. This is a true statement, right? So if you, instead of B, if you replace that true with B, we know this is true. The sun always rises in the east. So that is the same as saying A is equal to A. These are all equal. A equals A and true. If you replace true with B, the sun will rise in the east. We know that's true. That's equal. It's the same as saying Alice owns a dog. So A equals A and B. All right. So B or not B equals true for any events B. So, I mean, no matter how you write this truth table up, B is false or B is true, it's always going to evaluate the true because only one of them, think of the truth table, the OR operator, only one of them has to be true for this to evaluate to true. So if B is true, then it evaluates to true. If B is false, then not false evaluates to true. Okay, so that one's pretty obvious. All right, so here's an example. Suppose we have probability of A and B, let's say that equals 0.3, and probability of event A and not B equals 0.2. So we got to find probability of A. Well, we know A equals A and true, so probability of event A is equal to probability of A and true. And we also know B or not B is equal to true. So we could replace that true with B or not B. Let's use some boolean algebra here. So probability of A and true equals probability of A and B or not B. We know B or B is not true. Or excuse me, B or not B is true. So this is equal to probability of A and B or A and not B. That's using the boolean algebra from the previous videos, right? We essentially distribute that A. So, and then we change the and to an or. So probability of A and B, probability of A and not B, and then you put the or operator in between them. And now if we use probability algebra, A and B and A and not B, those are mutually exclusive events. So probability of X or Y equals probability of X plus Y for mutually exclusive events. So we can keep going with that. We do probability of A and B or probability of A and not B. So probability of A and which is equal to probability of A and B plus the probability of A and not B. Well, if we look up here in the original, in our problem, probability of A and B equals 3. So we can just substitute, right? So probability of A and B, we'll replace that with 0.3. Probability of A and not B equals 0.2. So we'll replace probability of A and not B with 0.2. 0.3 plus 0.2 equals 0.5. We use two things here, Boolean algebra and probability algebra. So Boolean algebra is what takes place inside the P operator, the probability operator. And then probability algebra is what is applied on the probability, the P operator. This is important to understand. There's lots of problems in quantum computing that are required, this is required to solve them.